Okay, in this video I was going to get back to the trig stuff here that we're covering in the review part of the class here. So we've done some calculations with basic angles, and I talked about the triangles and the unit circle a little bit in the last video. Let's take a look at the graphs of the trig functions. Now, I feel like it is important to know the graphs of the trig functions. We're going to be doing lots of things with graphing throughout the semester and also working with trig functions. So these 6 trigonometric graphs are really ones that you'd want to have memorized. Okay, we will be using them. And of course, be sure that you know the basic information, okay, like the domain, the range, the intercepts maybe, okay. And of course, there's no mystery about how I'm getting these curves, right? I'm selecting values for x and getting corresponding y values. So like if I were to let x be 0, well, 0 is a major angle, right? So sine of 0, well, sine of an angle is where I take y over r. Here's a radius of 1, okay? So 0 over 1 is 0, okay? So sine of 0 is 0. Sine of pi over 2, well, pi over 2, that'd be this axis right here. X is 0, y is 1. Y over r, well, 1 over 1 is 1, so sine of pi over 2 would be 1, that's right here. Sine of pi, okay, so here's the pi axis. X is negative 1, y is 0. Y over r, 0 over 1 is 0. Okay, and if I let x be 3 pi over 2, which I've already done, sine of 3 pi over 2 is negative 1. So here's 3 pi over 2, negative 1 on the graph. 2 pi radians would be 1 complete revolution around the circle, and that'd put you right back at the 0 radian axis. Sine of 0 is 0, so sine of 2 pi would also be 0. Of course, all 6 trig functions are periodic. The periodic factor for the sine function, the cosine function, and the reciprocals, the cosecant function and the secant function, is 2 pi radians. So what I see here on this interval 0 to 2 pi is going to repeat infinitely often. Okay? Same deal with the cosine curve and their reciprocals. Okay, now the tangent and cotangent functions are also periodic, but the periodic factor is pi radians for those curves. In other words, if I just look at the interval 0 to pi here, what I see on that interval is going to repeat infinitely often. Okay, same deal with the cotangent curve. Okay, what I see on the interval 0 to pi is going to repeat itself infinitely often in increments of pi. All right, I've got the domain and the range listed here. And again, these are graphs that you would obviously see in a trig class, and these are ones that I'd like you to have memorized. Okay. Now, of course, I can use the knowledge that I have about transformations to build many more graphs, right? Like if in problem 15 here, if I want to graph y equal negative sine x plus 2, well, I know I'm going to take the sine curve here as my basic function, and so I've regraphed that on this picture, and so the negative in front of the sine x means that you're going to rotate about x with all these points, and then the plus 2 at the end means that you're going to shift up 2 units. Okay, so there's 2 transformations that are going to happen here with this curve. Rotate about x and then shift up 2 units. So like here's 0, 0. If I rotate about x, that's not going to change where that's located, but then I'd want to shift that up 2 units, and that point now is going to be at 0, 2. Any intercept on this original graph is just going to be shifted up 2 units, right? So pi is 0 is going to be at pi 2, 2 pi 0 is going to be at 2 pi 2, etc. Here's pi over 2, 1. If you reflect about x, that'll put you at pi over 2, negative 1, but then shift that up 2 units, and that'll put you right back to where you started, which is pi over 2, 1. Here's 3 pi over 2, negative 1. Okay, when you reflect about x, that'll put you at 3 pi over 2, 1, and then shift that up 2 units. That'll put you at 3 pi over 2, 3 on the new graph. So I've got this curve here, and again, I can use the fact that the function is periodic with the periodic factor 2 pi radians. So what I see on the interval 0 to 2 pi is going to repeat infinitely often in both directions there. Okay, and I can produce the rest of the sine curve for y equal negative sine x plus 2. Okay, part B is another transformation type situation. So we can graph y equals 2 tangent x. Well, here's the graph of the tangent curve, okay, which is, again, a graph that I'd like you to know. So I've regraphed the tangent curve here. If I stick a 2 in front of that, all I'm going to do is I'm going to just simply multiply all the y values by 2 to get the new graph. So, 0, 0 is going to stay at 0, 0. Here's pi over 4, 1. When you multiply the y value by 2, that'll put you at pi over 4, 2 on the new graph. Okay, here's negative pi over 4, negative 1. When you multiply the y value by 2, that'll put you at negative pi over 4, negative 2 on the new graph. And the fact that I've got a 2 in front of the tangent function means I'm going to have a vertical stretch of the original graph. Okay, so this graph is going to get closer to the y-axis there on both sides. And I've drawn the new curve passing through these points. And of course, I can use the periodic factor here. The tangent function is a periodic function of pi radians. So what I see here on the interval negative pi over 2 to pi over 2 would be a length of pi radians, right? What I see on that interval is going to repeat infinitely often. Okay. Of course, there's asymptotes that are on this graph, right? Tangent of pi over 2 would be undefined, since here's the pi over 2 axis, y over x, well, x is 0, right? You can't divide by 0. Same thing with 3 pi over 2. Tan 3 pi over 2 is undefined, okay? 3 pi over 2 would be the same axis as the negative pi over 2 axis, right? Positive angle means that you're going clockwise around the origin. A negative angle means that you're going clockwise, okay? So it's just a directional thing. All right, so there's my, my graph of y equal 2 tan x. In calculus, we're going to be asked to prove things from time to time. I don't want you to be scared off by that word proof. In calculus, you're really going to get your first introduction to abstract mathematics and have to deal with proofs on occasion. Okay, a proof is just an argument about why something is true. Okay, so many times it just comes down to a computational thing. Okay, for this class, basically, we just want to show that this statement here is true for all theta. Okay, now, when you work with identities in trig, one of the things that I tell my trig students is that when it comes to identities, you shouldn't need to have all these identities memorized. Okay, there's really just kind of a handful, probably 5 or 6 identities that I'd like you to know. And I'll comment on those once we, well, actually, so the ones that I would like you to know would be the following here. I would like you to know the reciprocal identities. I don't know that you could call those identities. They're really by definition, and we've been using it. The reciprocal of sine theta is cosecant theta. Or cosecant theta would be defined as 1 over sine theta. Secant theta would be defined as 1 over cosine theta. Cotangent theta would be defined as 1 over tangent theta. Okay, those are the reciprocal identities. Tan theta is defined as sine theta over cosine theta. Okay, that's an identity that is worth knowing. But then there's our Pythagorean identities. All right, so there's 3 Pythagorean identities that we should know. The first one says that sine squared theta plus cosine squared theta is 1. The second one, secant squared theta minus tangent squared theta is 1. And then the third one, cosecant squared theta minus cotangent squared theta is 1. I would like you to memorize all three of these, okay? They do come up a lot, and they're just worth knowing. We use them for, simplifying purposes. And really, that's all you need to know with identities, okay, at this point, okay? Now, you'll be doing lots of trig, as you continue on with calc, and so there are some identities that you'd want to eventually memorize, later on, but that's really it. So, like, this isn't an identity that you'd use over and over again. It's really just a verification that this is true for all theta. Okay. Now, when we prove an identity, typically we start with the side that's more complicated, and we work our way over to the other side using the identities that we do know along with algebra. Okay. So the left side is more complicated than the right side, or more involved. I shouldn't say complicated, but it's got more going on in it. So it makes sense to begin with the left side. Now, I'm not solving for theta or solving for x or anything like that. Okay, don't think of the problem like that. I'm just simply starting with one side, and I'm using what I know about algebra and simplifying and the identities that I should have memorized, and I'm going to algebraically manipulate this down to what I see on the right side here. Okay, so let me do that. The first thing I'm going to do here is I'm going to rewrite the left side so that it's all in terms of sines and cosines. That can be a good strategy. Okay, tan theta is the same as sine theta over cosine theta. Cotangent theta, that's the same as cosine theta over sine theta. Inside the parentheses, I'm going to combine this to a single fraction. Okay, my common denominator would be sine theta cosine theta. Cosine squared theta plus sine squared theta is what I get in the numerator. Now, cosine squared theta plus sine squared theta is 1, right? That's one of my Pythagorean identities here. And so I'm going to get 1 in the numerator. Sine theta over sine theta, those are going to cancel for me, and I'm going to be left with 1 over cosine theta, which by definition would be how we define secant theta. Okay, and that's where I had to get to, right? I had to get to the, just secant theta there on the right. And so what we see here would be the proof of why this identity would be true for all theta. All right, let's take a look at problem 17. Solving trig equations is big, okay? Let's take a look at, I got 2 trig equations that we're going to be solving. Part A, let's solve 2 cosine theta minus 3 equal negative 2. Okay, well, if you add 3 and then divide by 2, you're going to have cosine theta equal 1/2. Now, there's going to be infinitely many answers here to this problem if I were to just let theta be anything, okay? Because cosine of an angle is adjacent over hypotenuse. So I can build my triangle. The adjacent side is 1, the hypotenuse is 2. That means the leftover opposite side would be root 3. And the angle that we would be talking about there would be a 60-degree angle. Okay, give the answer in a radian measure. I've already mentioned that, more times than not in calculus with the trig stuff, you're going to be doing things in radian measure. Okay, so keep that in mind when you're going through this stuff. Okay, so pi over 3 would be one answer. Now, if I were to flip this triangle over into quadrant 4, the adjacent side is still 1, the hypotenuse is still 2, the opposite side is negative root 3, which I don't care about for cosine theta, right? Cosine theta is adjacent over hypotenuse. Now this angle would be 5 pi over 3 radians. Okay, so 5 pi over 3 would be another answer that I'd want to give. Now if I were to flip this triangle over into quadrant 2 or quadrant 4, then that's going to affect the adjacent side. The adjacent side is going to be a negative 1, and I don't want that. I want the adjacent side to be a positive 1. Okay, so I'm only going to be building triangles in quadrants 1 and 4. Now, I can have infinitely many radial lines that are going to be right at the same spot as pi over 3 and 5 pi over 3. Okay, in other words, the 7 pi over 3 radial line would be the same spot as the pi over 3 radial line. Let's see here, the 11 pi over 3 radial line would be at the same spot as the 5 pi over 3 radial line. Okay, so etc. So you're actually going to have infinitely many values for theta. Now, because a lot of the trig equations would end up going like that, you know, where you're going to have infinitely many answers, to avoid every single situation being, well, there's infinitely many answers, usually we just say, okay, solve the equation on the interval 0 to 2 pi. Okay, so if we're only on the interval 0 to 2 pi, my only two answers then for theta would be pi over 3 and 5 pi over 3. If theta can be anything, then of course I'm going to have pi over 3 and then anything that would be 2 pi radians beyond that. Okay, same thing with 5 pi over 3 and then 2 pi radians beyond that. So there'd be, you know, you'd be producing infinitely many answers in that situation. Part B, solve the equation here. Okay, now this is a trig equation. That's obvious, right, because of the sine theta that we see. But we can also call this a quadratic equation. The reason is because of the form that this is given in. Right, I've got a squared term, a linear term, and a constant all added to be 0. Well, that very much resembles a quadratic, right? A quadratic is ax squared plus bx plus c equals 0. Now, if I were to let u be sine theta and square both sides, u squared would be sine squared theta. So I'm going to have a 2u squared term leading off minus 3. U is what we're calling sine theta, so it'll be a minus 3u, and then plus 1, that's all equal to 0. Okay, and by making that substitution there, I can see more clear now that I had a quadratic kind of hidden in disguise a little bit. Okay, here it is in terms of u. So knowing that I've got a quadratic means that the next thing that I'd want to do is to factor the left. The left side should factor nicely as 2u minus 1 times u minus 1. Set the factors equal to 0 and solve, okay, and you'll get u equal 1/2 or u equal 1. Now here's the thing, we don't care what u is, we care what theta is, right? U is just a temporary thing that I used here to help me see that I actually had a quadratic going on in the calculation. So I'm solving for theta though. So that means that the next thing I want to do is to substitute back. Okay, u is sine theta, so I'm going to say sine theta equal 1/2. Or sine theta equal 1. Sine theta equal 1/2. Well, sine theta is defined to be opposite over hypotenuse. So if they build this triangle here, the opposite side is 1, the hypotenuse is 2. That's going to mean the left over adjacent side would be root 3. Okay, this is one of my common angles. This is a 30-degree angle, right, or pi over 6 radians. So pi over 6 is going to be one answer that I would give here. Now, if I were to flip this triangle over into quadrant 2, sine of 5 pi over 6 would also be 1/2, right? Because the opposite side is 1, the hypotenuse is 2. The adjacent side is negative root 3, which I don't care about for sine theta, right? Sine theta is opposite over hypotenuse. I'm not doing anything with the adjacent side there. So 5 pi over 6 would be another answer that I would give. Now, if I were to flip either of these triangles into quadrants 3 or 4, then the opposite side would be a -1, so I don't want that. I need the opposite side to be a +1. All right, so we're going to only have these two angles here on the interval 0 to 2 pi. How about sine theta equal 1? Okay, well, sine of pi over 2 is 1, right? We've already looked at that. And if you're only on the interval 0 to 2 pi, that's going to be the only angle where sine of that angle is 1. So in all, theta would be pi over 6, 5 pi over 6, and pi over 2. Of course, when you're solving a trig equation, make sure that you get all the answers. Okay, like I'll see students sometimes just write pi over 6 and pi over 2. Like they didn't consider this triangle being, flipped over into quadrant 2 here. Make sure that you get all the answers Of course, it's, if it's incomplete, it's not, you don't have the correct answer then.